In the last video, we calculated the enthalpy change for a reaction by taking the heat that the reaction had generated and dividing it by moles of limiting reactant. But what really did we calculate there? What is enthalpy? It's a little bit more than just heat per mole. The definition of enthalpy change. The change in enthalpy is heat released or absorbed by a process. Now I'm going to say process instead of reaction because this can work with things that are not chemical reactions as well. Phase changes, for example. Mechanical processes. There can be other things that can happen that can have an enthalpy associated with them. Here's the important part. Constant pressure. We didn't say anything about that when we were doing our calculation before, but it's got to be at constant pressure. Well, let's see what's going on here. Suppose I've got a flask, and I've got some kind of reaction, maybe a combustion reaction or something going on in here. And I have a nice stopper on top, and there's no air or anything. There's only the reactants of the reaction in here. So the reaction is producing some heat. Let's say it's a reaction that produces heat. If I calculate Q for this reaction with some kind of a calorimetry experiment, maybe I find it's minus 100 joules. Now I've run the reaction in a constant volume situation. And the first law of thermodynamics that we talked about earlier in the last worksheet is heat plus work. Now, because you're at constant volume here, no work is done. There's no work being done here. Nothing is moving, really. And the heat that you get out there is the change in energy. So we can say the change in energy for this reaction is minus 100 joules. Another way to say that is this reaction releases 100 joules of heat. Now what if we did something very simple, like taking the exact same reaction, the exact same amounts of everything. It's a reaction that produces heat, and I open the top. Now you might think, well, some of the heat is escaping, but suppose I have this arranged so that heat can't escape up there. Maybe I do this very quickly so that heat doesn't have a chance to escape. But this is a constant pressure situation. Now, I might measure with a calorimetry experiment the amount of heat that comes out of the reaction. And I might get something like this. A little bit less heat is released. Now, where did the extra energy go? Because the reaction is producing the same amount of energy here as it is here. So I should get Q equals minus 100. And you're not just losing heat through the top here. Now what you're doing is you are pushing against the atmosphere because atmospheric pressure is coming in, and that's what makes it constant pressure. So in this situation, the work, the reaction is actually expanding against the atmosphere, pushing back the atmosphere. And this is the amount of work that leaves the system to push back the atmosphere, to expand. So it's very difficult for us to measure the amount of work because we'd have to measure the volume change of this system. And when the top is open like that, it's not really such an easy thing to do, always. We would like to have some way of avoiding calculating that work every time from the volume change that the reaction undergoes. So what we do is we define the enthalpy change as the heat, and sometimes we could put a subscript P here for heat absorbed or released at constant pressure. So the enthalpy change in this case is going to be minus 99 joules. Now we can just use enthalpy changes for reactions from now on instead of using energy changes. And that way we don't have to worry about the work. And as long as we consistently use enthalpy changes when we're looking at reactions, when we're studying how reactions go, we're going to be fine. So this is just a simplification using enthalpy change rather than energy change. And this really is the difference between the two. This would be a good essay question on a test. What is the difference between the enthalpy change and the energy change? And you would say the energy change is the amount of heat you get at constant volume. The enthalpy change is the amount of heat you get at constant pressure. Now, if you take a look at the sign on the enthalpy, it's pretty important. If you've got a minus sign on delta H, that means heat is being released. Think about reactions that release heat, like a fire. A fire releases heat into the atmosphere. There's no such thing as a cold flame. It's always a hot flame, and it's releasing heat. So you always say a negative delta H on a combustion reaction, for example. When you've got a positive sign on delta H, it means heat's being absorbed from the surroundings. And in that case, it'll feel colder. And reactions like that are a little bit rarer, but they do occur. Some of these reactions that occur in a chemical cold pack are like that. Now, there's a name for these two situations. If you have a negative sign on your delta H and heat is being released, they call that an exothermic reaction. So this would be an exothermic reaction that we have in here because it's got a negative sign on the delta H. If we've got a positive sign, it's called endothermic. So these are two vocabulary words that you should know. In the next video, we're going to talk about where the heat actually comes from in the reaction. What about the reaction produces heat or absorbs heat?